Here I'm going to look at a statistics question from Leaving Cert 2018, paper 2, question 8. It starts off with a confectionery company with a new chocolate bar. Now the weights of the bars are normally distributed with a mean of 4.64 grams and a standard deviation of 0.12. A sample of 10 bars is selected at random. And the mean weight of the sample is found. So here this tells me straight away that we're dealing with sample means. So this is where we take samples of our original population and get the mean of them. So they found the mean weight of the sample. Find the probability that the mean weight of the sample is between these two values. So what we're going to do here, we're going to create some z-scores based on these new mean values of our sample. I'm going to use what's known as the test statistic, and you can see here the test statistic, it's called t-test here, but the test statistic allows us to take random samples and create a z value from those random samples, taking into account a margin of error, so the sample size and the standard deviation. So our test statistic there is going to be x minus mu, so that's our individual score minus the mean divided by our standard deviation over the square root of the sample size. Let's call this Z1, Z2. We're going to create two here. So Z1 is going to be 4.6 minus the mean, which is 4.64, over 0.12 divided by root 10. So we plug that into our calculator. We know that it's less than a mean, so it's going to have a negative z-score because you've got a negative number over a positive one. And that gives us the result of minus 1.054095. So minus 1.05409 for that one. Our second z-score is now going to be 4.7 minus 4.64 all over 0.12 divided by root n, and that's going to give me a result of 1.5811388. So what I'm looking for here is the probability of finding a value, i.e. a z-score, in between 1.58 and minus 1.05. So if we just draw that out, we have a result which is 1.58 and we have a result which is minus 1.05. When I look up the z-score for 1.58, I get all this information, which is the probability of finding a z value less than 1.58. So I need to subtract everything that's here, and to look up all of the information in green there, what I actually need to do, look up 1.05, positive version of that. I want all the information to the right of that, because that pink amount should be the same as, if it was drawn correctly, the green amount, which is the one I want. So technically I want to find the area to the right of 1.05, but when I look up the z tables it gives me a result which is less than 1.05, so I need to subtract it from 1 to get that accurate value. So when I look up 1.58 I get this figure here. That's 94.08% of all the data lies to the left of that figure, so it's going to be 0.9408 minus 1 minus the figure I look up when I get 1.05. And when I look up 1.05, I get 0.8531. So 0.8531 tells me all the information to the left of that line. So I want the information to the right. So it's going to be 1 minus that. And that, when I plug that into the calculator, it gives me a result of 0.796, okay, or 79.6%. That is the probability that the mean weight of the sample is between those two figures. Okay, so quite likely there. This next question then deals with, you've got a survey of 400 people, so this is probably going to be population proportion, so we'll just need to know that for which formula to use. 400 people were surveyed. (324), so they like the new bar, create a 95% confidence interval for the proportion who like the new bar. Okay, so the confidence interval for that is going to be p hat plus or minus 1.96 times the square root of p hat times 1 minus p hat all over n. So you got 324 out of the 400 liked the bar. So p hat here is the sample proportion. So that's going to be 324 over 400. So you can work that out as a decimal. If it doesn't work out too neatly, you can just leave it as a fraction, but it's 0.81. So the confidence limits are going to be 0.81 plus or minus 1.96 times root 0.81 times 1 minus 0.81, which is 0.19, all over n, which is 400. So when we're creating a confidence interval, we're saying with 95% confidence that the result will be between 0.81 plus this figure and 0.81 minus that figure. So when you plug those into a calculator, you get a result of 0.7716 less than p less than 0.8484. Overall there, it says to 2 decimal places, so our answer to 2 decimal places is 0.77 less than or equal to p less than or equal to 0.85. So that's with 95% confidence that between 77% and 85% of the population like the chocolate bar. Okay, put a tick into the table for each statement to indicate whether it's always true, sometimes true, or never true. So what we're going to do is I'm just going to bring this back down here. Okay, when forming confidence intervals for a fixed n and p hat, an increased confidence level implies a wider interval. Well, an increased confidence level means that this gap between p gets bigger and bigger, so it's always going to be a wider interval there. As the value of p hat increases for a fixed number n, the estimated standard error of the population of the proportion increases. Well, we see the p hat is there. P hat is just the sample proportion. The sample proportion will sometimes change, but it won't always change, and it's not that it'll never change. So sometimes it will change, so this has to be a sometimes. As the value of p hat times 1 minus p hat increases for a fixed n, the estimated standard error of the population proportion increases. So basically they're saying as this numerator increases, then our standard error, which is this range here, increases. Well, if that numerator increases, then yes, it's always going to increase. as n the number of people in the sample increases for a fixed p hat, the estimated error of the population increases. Now it's saying that if the denominator increases, then the error increases. Well, as the denominator increases, the error decreases, because we want more people in our sample. That means there's less margin of error. So if there's less margin of error, then that's never true. Using calculus or otherwise, find the maximum value of p hat instead of 1 minus p hat. It says using calculus, okay? We know using calculus, we know that from any function to find the maximum value of it, then we derive it and let it equal to 0. So we know that p hat times that all over n is equal to error, so let's call it the error. The error is equal to that, so what we want is to find the maximum, so that how the error changes with respect to p hat. Okay, I know it's not quite the error, but we'll call it that. That's going to be the derivative of this. So to derive that, we'll expand the bracket, so you've got p hat minus p hat squared. The derivative of that is just going to be 1 minus 2 times p hat. Okay, when we derive that, we let that equal to 0, so therefore 2 p hat equals 1 p hat is equal to a half. So if p hat is equal to half, the maximum error, or the maximum value there, is going to be a half times a half which is a quarter. So in the last part here, for this section, find the largest value of the radius at a 95% confidence interval for a sample of 800. Well, p hat we said is a half, so it's going to be 1.96 over 1 half times 1 half over 800, which is equal to, so you just plug that into the calculator and that gives you a result of 0.034648. So it's 3.46%. Just to finish this, there's a finance question here. The confectionery company has an employee pension plan. For an employee who qualifies for the full pension, they'll pay a sum of 20,000 on the day of retirement. It will then pay a sum on the same date each subsequent year for 25 years. Each year the employee is paid a sum that is 1% more than the amount paid the previous year. What sum of money must the company have set aside in order to fund this? We're going to be looking at a geometric sequence here. We know that on day 1 they need to pay 20,000. The following year they need to pay 20,000 times 1.01, because that's a 1% increase. But because for any future value, it's going to be the present value divided by the interest rate, because if you think about it, if they're paying out the sum of money in a year's time, well, at the moment, that sum of money is going to be worth a little bit less. i.e., the amount of money they need to save right now is going to be less, because in a year it will have grown by its interest rate. So we need to divide that by the amount of interest it's earned, and it's earned 2.4%, so it's going to be 1 plus I, which is 1 plus 2.4%, which is 1.024. So that's that first year. Then the next year it's going to be 20,000 again, but it's going to have grown by 1.01 again. That's squared, and also it's now going to be worth even less because it's been in for 2 years. So what you can see is we're creating a geometric series here, and the final payment is for 25 years, so the final payment is 25 years later. So we have 1.01 to the 25 over 1.024. So what we can do is we can take out the common term, so it's going to be 20,000 outside of 1 plus 1.01 over 1.024 plus 1.01 squared, all the way up to 1.01 to the 25 over 1.024 to the 25. So that here, for this part, we can create our geometric series. Looking here, there's 26 terms, so sum of the first 26 terms is going to be equal to, if we look at the formula in the tables for that, it's going to be a outside of 1 minus or to the 26, or to the n, over 1 minus or. And here we have a is the first term, 1, and or, it's increasing by 1.01 over 1.024 every time. So in total our answer is going to be 20,000 outside of 1 times 1 minus 1.01 over 1.024 all to the 26 over 1 minus 1.01 over 1.024. And we plug that into the calculator and we get a result of 440,132, 440,132.4015. So that is the amount that they need to now save in order to pay that retirement plan.